Hi, everyone. In this video, I want to go through some of the problems, the classwork problems for section P.3. Section P.3. So in problem number one, we want to evaluate the expression, the square root of 144 plus 25. So I want to just, before we do this problem, I want to just remind everyone that we have this rule, this property of square roots, that the square root, or any root, not just square root, but any root of a times b is equal to the square root of a times the square root of b. So for example, if we have the square root of, let's say, 32, well, that's equal to the square root of 2 times the square root of 16, because 2 times 16 is 32, right? Now, the square root of 16 is a perfect square, so we can keep going and say, well, this is the square root of 2 times 4, because the square root of 16 is equal to 4. And we would give our final answer as 4 times the square root of 2. Okay, so when you have multiplication, you could split up the square root. What we do not have a rule that says the square root of a plus b is equal to the square root of a plus the square root of b. This is not true. Right, this is not true. So if we look at this problem, 144 is 12 times 12, and 25 is 5 times 5. So if you were to say this is the square root of 12 plus, the square root of 12, the square root of 144 plus the square root of 25 is equal to 12, which is the square root of 144, plus 5, which is the square root of 25, and 12 plus 5 is equal to 17. Well, this would be wrong. This would be incorrect. Right? There is no rule that says you can split up a square root with addition and subtraction. Okay? So you cannot do the square root of 144 separately and the square root of 25 separately. Right? What we have to do in this case is say, well, under the square root, 144 plus 25 is 169. And since 13 times itself, 13 squared is equal to 169, the answer would be 13. Okay? So keep in mind, you could split up a square root with multiplication or division. You cannot split up a square root with addition or subtraction. Okay, problem number 2. Simplify the expression. Assume that all variables represent non-negative real numbers. So x is not a negative number. Okay. So let's start with the number 45. What we're looking for when we take the square root of a number are perfect squares. So 1 squared is equal to 1. 2 squared is equal to 4. 3 squared is 9. 4 squared, no, it's 4 squared. 4 squared is 16, so on. 5 squared is 25. 6 times 6 is 36. 7 times 7 is 49, and so on. Let me say just dot, dot, dot. We could keep going. 8 times 8 is 64. 9 times 9 is 81, and so on. So what we're looking for in the number 45. So 45 is not a perfect square, right? If you take the square root of 45, you don't get a whole number. But one of these perfect squares is a factor. Oop. One of these, I meant to do a highlighter there. So the number 9 is a factor of 45. So 45 is equal to 9 times 5. So when we have the square root of 45x to the 5th. Well, let me write this in a more expanded form. All right, so 45 is 9 times 5. Okay, and what does it mean x to the 5th? That means 5 copies of x. X times x times x times x times x. So x times x times x times x times x. That's x to the 5th. So what I have down here is just a more sort of a more expanded way of writing the 45x to the 5th. So now we could take the square root of 9, right? The square root of 9 is 3. We know that. And x times x, well, that's x squared. So if x is not negative, then the square root of x squared is equal to x. And then we have another pair of x's. So basically, the degree of the root, in this case, it's the square root. The degree of the root is basically the number of copies you need to evaluate that square root. All right, so we can take the square root of 9. That's going to come out. We could take the square root of x squared, or x times x. That's going to come out. And the second x times x, that's going to come out. So on the outside, square root of 9 is 3. Square root of x squared is x. Square root of the second x squared, that's another x. And then left on the inside, we've got a 5 and an x. Okay, so, and we could sort of compact this a little bit. 3 times x on the outside, that's going to be 3x squared. And then inside the square root, we're still left with a 5 times x. 5 times x. So that would be the final answer, 3x squared. That's we're basically pulling everything we can out of the square root. Square root of 9 is 3. Square root of x squared is x. We got 2 of those. So that gives us x squared on the outside. Okay. Number 3, simplify the expression. And again, assume, well, in this case, assume that all variables represent positive real numbers. So x is a positive number. So what we could apply here, we have this property that says the square root of something divided by the square root of something else. So I'll say the square root of a over the square root of b. The a would be the 150x to the 4th, and the b would be the 3x. Okay, so the square root of something over the square root of something else equals, we could combine the square roots under one fraction, or of one fraction. So 150x to the 4th over 3x. So let me just write that in a more general form. Square root of a divided by the square root of b is the square root of a over b, or the fraction of square roots is equal to the square root of the fraction. So if we look at this problem, we have the square root of 150x to the fourth divided by the square root of 3x. Now we could write this as a single square root. 150 x to the fourth over 3x. Now, 3 is a factor of 150, meaning 150 is equal to 3 times something. So 150, we could say that's 3 times 50. And we've got a 3 on the bottom. All right, so ignore the variables for a moment. 150 on top, 3 on the bottom. Well, the 150 is 3 times 50. Now, x to the fourth means we have 4 x's. 1, 2, 3, and 4. Okay, on the bottom, we've got 3 times x. So any number divided by itself is equal to 1. So 3 over 3, that's equal to 1. X over x, that's equal to 1. So the 3's cancel. One of the x's on top cancels with one of the x's on the bottom. So the entire denominator, the bottom of the fraction, cancels. So we're left with the square root of 50 times x times x times x. And we can take this one step further, break it down one step further. 50, let me go back to the problem. 50 is equal to 2 times 25. Right? 50 contains a perfect square. So 50 is 2 times 25. We still have 3 x's down there. So now we could take the square root of 20. Oh, sorry, didn't mean to do that. That was supposed to be highlighter. One more try. There we go. We could take the square root of 25, and we could take the square root of x squared, which is x times x. So the square root of 25 is 5. And the square root of x squared is x. So basically, this square root of 25 comes out, and the square root of x squared comes out. And still under the square root, there's a 2, and there's an x. So we have the square root of 2x. So our final answer would be the square 5x times the square root of 2x. Okay, so that does it for number 3. Number 4, rationalize the denominator. So before we do this problem, let's say you're working through a problem. You work through all of the steps. You do your solving and you're simplifying and collecting like terms, and then your final answer, you say x is equal to 4 over 6. Well, this is not an acceptable final answer because this fraction, 4 over 6, is not reduced, right? So conventionally, you're not allowed to leave an unreduced fraction as your final answer. What you would do is say, okay, well, x equals, well, 4 is 2 times 2, and 6 is 2 times 3. And then, well, those 2's will cancel. And you would say, okay, well, the reduced fraction would be 2/3. All right, so one of the rules of mathematics conventionally is your final answer, if it's a fraction, should always be in reduced form or simplified form. Simplified form. Okay? So when our fraction contains square roots, we have a similar rule, just like your final answer, if it's a fraction, has to be reduced. Well, your final answer, if it's a fraction with square roots, the rule is no roots in the denominator. All right, no roots on the bottom of a fraction. So we have to, for this to be considered simplified or reduced, we have to get rid of the square root of 5 on the bottom. There cannot be a square root of 5 on the bottom. On top is okay. The square root of 2 on top is fine. It's the bottom. It's the denominator. We cannot have a root on the bottom. So we have to get rid of that somehow. Now, this is not an equation. There's no equal sign. If there was an equal sign, you have a lot more freedom. You could do anything you want as long as you do it to both sides. This is an expression. So there's only really a couple of things you could do to an expression that doesn't change it. You could add 0. Anything plus 0 equals itself, right? So you're allowed to add 0. That's it. You can't add anything else. So anything plus 0 equals itself. That doesn't help us. You could also multiply by 1, right? Anything times 1 equals itself. That you're allowed to do. But those are really the only two things you're allowed to do that don't change the value of this number. So what we're going to do is we're going to multiply by 1. And instead of using the number 1, we're not going to say times 1 like that. We're going to use the fact that any number over itself, x over x, where x could be anything, 2 over 2, 7 over 7, 1.5 over 1.5, it doesn't matter. Any number divided by itself is equal to 1. So we're going to use something that looks like this, x over x, something over itself. For this problem, we need a perfect square on the bottom. 5 is not a perfect square, right? So the square root of 5 is not a whole number. We need the square root of something on the bottom that will give us a whole number. So what we could do is we could multiply the bottom by another square root of 5. Right? Because what is the square root of 5 times the square root of 5? That is the square root of 25. And the square root of 25 is a whole number, right? The square root of 25 is 5. But we can't just multiply the bottom because that changes the meaning of this fraction. What we have to do is multiply by 1. So whatever number we use on the bottom, you pick that first. You pick the number on the bottom based on what you need. And whatever you do on the bottom, you got to do also on top. So this is equal to 1. That's why we're allowed to do this, because any number over itself is equal to 1. And if you times something by 1, you're not changing it. You're just changing what it looks like. For example, if you give someone a $1 bill and they give you 4 quarters, the 4 quarters look different, but they mean the same thing. Okay? So on the bottom, square root of 5 times square root of 5. On the top, we got the square root of 2 times the square root of 5, which is the square root of 10. Okay, so on top, that's fine. It's fine to have a square root on top of a fraction. We have the square root of 10, and on the bottom, square root of 25 is 5, and that's what we want. No roots, no square roots, no cube roots, no fourth roots, no roots at all on the bottom or the denominator of a fraction. Okay, the next problem, similar, but we have to approach it in a slightly different way. Again, rationalize the denominator. If we look back at the last, number 4, number 5, same directions. Rationalize the denominator, okay? So this word rationalize literally means eliminate any roots in the denominator. All right, the word rationalize means get rid of any roots, square roots, third roots, fourth roots, whatever the degree is. No roots on the bottom of a fraction. So we got to get rid of that square root of 11. Now, we can't do the same thing we did in the last problem because of that 3, right? We have 2 terms on the bottom here, 2 terms. So what we're going to use is what's called, so let me give you the definition, the conjugate. The conjugate of A plus B is A minus B. Right? The conjugate of a binomial, meaning 2 terms, A plus B, something plus something. In this case, the A is 3, right? So this is our A, and the B is the square root of 11, right? The conjugate of A plus B is A minus B. The reason we're going to use the conjugate is because that is the only thing you could multiply this by, which will eliminate the square root. So what we're going to do is A plus B times A minus B. So if we multiply this out, we have to do A times A, which is A squared. We have to do A times a minus B. So I'm using FOIL method here, F-O-I-L. First, outer, inner, last. So A times A, first times first. Outer times outer, A times a minus B. That's a negative AB. Usually put our variables in alphabetical order, right? Then we do inner times inner, which is B times A, which is the same as A times B. So plus AB. And then last times last. B times a minus B. So that'll be a minus B squared. So when you multiply a sum of 2 things, 2 numbers, 2 variables, two expressions, by its conjugate, you get A squared minus AB plus AB minus B squared, and the minus AB and the plus AB, they cancel. This is why we're using this. This is the reason why we have to use the conjugate, because this simplifies to the perfect square, A squared, minus the perfect square, B squared. So we have 2 perfect squares, meaning if you take the square root of a perfect square, square and the square root cancel out. Okay, so let's apply this to this problem. All right, we've got 13 divided by 3 plus the square root of 11. Now I'm going to go back to the previous problem just for a moment. Okay, number 4. When we did this, we're multiplying by 1 because anything over itself is equal to 1. We're going to do the same thing. We're going to do the same thing in number 5. We're going to multiply by a fraction where that fraction is something over itself. But we're going to use the conjugate. So we're going to multiply by 3 minus the square root of 11 over itself. So 3 minus the square root of 11 divided by 3 minus the square root of 11. Anything divided by itself is still equal to 1. So we're allowed to do this because we're in essence, we're timesing by 1. Okay, so let me throw in some parentheses just so we make sure we're doing things correctly. So on top, the 13 is going to hit the 3, and it's also going to hit the square root of 11. You're distributing the 13. So 13 times 3 is 39 minus 13 times the square root of 11. Well, that's just 13 square root of 11. And so that's the top of the fraction. All right, 13 times 3, and then 13 times the minus 11, minus square root of 11. On the bottom, we have to FOIL this out. So the 3, this 3 has to multiply to both of those guys. And then the square root of 11 has to multiply to both of those guys. So first times first, 3 times 3 is 9. Okay, outer times outer, it's a positive times a negative, so it's a minus. 3 times the square root of 11. Right? Inner times inner is positive. Both of those are positive, so that's plus 3 times the square root of 11. And then last times last, positive times negative is a negative. And 11 times 11 is 121, square root of 121. Right? So this gives us, it looks a little complicated at first, but on the bottom of the fraction, that's just a whole number. That simplifies to a whole number. Because the negative 3 square root of 11 cancels out with the positive 3 square root of 11. And the square root of 121 is equal to 11. So what we end up with, on top, we've got 39 minus 13 square root 11. And on the bottom, we still got that 9 in front. Cancel, cancel, minus 11. I'm going to need a little bit of extra room here, so let me do that. Okay. So now we just have to simplify. We know 9, we could do 9 minus 11. We know that. 9 minus 11 is negative 2. We could simplify this a little bit. We could rewrite this using one less symbol. We don't need a -2 on the bottom. This minus sign, we could actually bring that out front of the fraction. 39 minus 13 root 11. So we're minusing the whole fraction over 2. So what we basically want to do here is take that, we don't usually leave a minus sign on the bottom of a fraction. If we move that basically to the top, right? If that minus sign affects the top, the 39 becomes negative and the 13 square root of 11 becomes positive. So we could actually rewrite this as 13 times the square root of 11 minus 39, all divided by 2. So I think this is as simplified as we could get. Nothing cancels, nothing reduces. I mean, we could factor out a 13 on top, but I'm not going to do that for this problem. So yeah, 13 square root of 11 minus 39 divided by 2. Okay, so for number 6, so far, all of the roots have been square roots. In this case, we have the 5th root. But I'm going to generalize the property from a few slides back. I said the square root of a divided by the square root of b is equal to the square root of the fraction a over b. Well, this is not just true for the square root, it's true for any root. So if I put an n here, that n could be anything. It could be the square root, the 3rd root, the 4th root, the 5th root, the 10th root. It doesn't matter. In this case, it's the 5th root. So the fraction of roots is equal to the root of the fraction. So if we take the 5th root of 64x to the 6th and divided by the 5th root of 2x. The rule is the root has to be the same, top and bottom. It can't be the 5th root on top and the 4th root on the bottom, or the 5th root on top and the square root on the bottom. It's got to be the same degree, top and bottom. So we could rewrite that as the 5th root of 64x to the 6th divided by 2x. So now forget about the root. Just look at the fraction. 64 x to the 6th over 2x. Just look at that fraction. Well, 64 over 2. 64 divided by 2. Remember, fraction means division. So 64 divided by 2 is 32. And x to the 6th on top and x on the bottom, well, that 1x on the bottom cancels one of those x's. You got 6 x's on top. That's what x to the 6th means. X times x times x times x times x times x. You got 6 x's on top. One of those 6 will cancel with the 1x on the bottom. So you're left with x to the 5th power. All right, so underneath that 5th root, that fraction now cancels. The 64x to the 6th over 2x cancels, simplifies to 32x to the 5th. So the fifth root and the fifth power, they cancel each other out. And it turns out the number 32 is 2 times 2 times 2 times 2 times 2, which is 2 to the fifth. So 32 is equal to 2 to the fifth power. So this is actually the fifth root of 2 to the fifth times x to the fifth. All right, so the fifth root and the fifth power, they cancel each other out. In the same way, a +3 and a -3 cancel each other out. So when we reduce this or simplify this, the fifth root of 2 to the fifth is 2. And the fifth root of x to the fifth is also, they cancel. Fifth root, fifth power, cancel. So we get x. So our final answer here will be 2x. All right. So that does it for number 6. Now, the last one, evaluate the expression without the use of a calculator. We got to show our work here. So there's a couple of exponent rules that apply here. So let's start with that. The first rule that applies is the negative sign. So anything, let's say x can be anything, right? X raised to the negative a. X raised to the negative a. So in this case, the x is the 32 and the a is the 4/5. So something raised to the negative something is equal to 1 over, it's the reciprocal. So the negative exponent means reciprocal. So that's x to the negative a is 1 over x to the power of a. And if the negative starts on the bottom of a fraction, same thing. We take the reciprocal, so it moves to the top. So basically, if you have a negative exponent, you move it to the other side of the fraction bar. If it's on the top, you put it on the bottom, it becomes positive. If you have a negative exponent on the bottom, you move it to the top, and it becomes positive. So the first thing we could do is say 32 to the negative 4/5 power is equal to 1 over 32 to the positive 4/5. All right, so that's how we deal with the negative sign in the exponent. We just put it on the bottom of the fraction, it becomes positive. The second exponent rule that applies here is if you have some number raised to a power, and that power is a fraction, so x to the a over b, like 32 to the power 4 over 5. That is equal to x to the power of a with the root, with the degree of b. So power, basically, think about it like this. The exponent is power over root. A is the power, b is the root. So if we have 32 to the power 4/5, 4 is the power, and 5 is the root. Power over root. So fourth power, fifth root. Well, we saw in the previous problem that 32, so I'm right here, 32 is equal to 2 to the fifth power. 32 is 2 to the fifth. So 32 is 2 to the fifth, but there's still a fourth power there. So instead of saying 32 to the fourth, that's 32, or that's 2 to the fifth, which is 32, raised to the power of 4. So now we can apply another property of exponents. If you have something raised to a power that's then raised to another power, like 2 to the fifth to the power of 4. So if you have a power to a power, you multiply the powers. You multiply the exponents. That's x to the a times b. So this is 1 over the fifth root of 2 to the 20th power. Okay. We're almost there. We're almost there. Give myself a little bit more room here. Now we have to take the fifth root of 2 to the 20th power. Well, the fifth root is saying every 5 copies under the root is equal to 1 copy on the outside. So every 5 twos, right? We have the fifth root. So every 5 twos under the root in here, every 5 of them is equal to a single 2 outside of the root. So how many groups of 5 do we have? Well, we have 20 twos. I'm not going to write 22s out, but there's 20 of them. Every 5, so we're basically, maybe I'll write it like this. The fifth root of 2 to the fifth times 2 to the fifth times 2 to the fifth times 2 to the fifth. That's 20, a total of 22s, right? 5, 10, 15, 20. So there's a group of 5, a group of 5, a group of 5, and another group of 5. So this, just this by itself, what I just circled in red, the fifth root of 2 to the fifth, right? The fifth root of 2 to the fifth is equal to 2, just 2 by itself. And that's happening 4 times. So we've still got that 1 on top. And on the bottom, we've got 2 times 2 times 2 times 2. Each one of those 2 to the fifths, when you take the fifth root, gives you a 2. 2 times 2 times 2 times 2 is 16. 2 times 2 is 4, times 2 is 8, times 2 is 16. So our final answer. There's a lot going into this, is that there's 3 or 4 different properties of exponents, but our final answer will be 1/16. Okay, that does it for this problem, and that does it for this problem set. I hope this was helpful.